Hey, what is going on? What is up? It is Tuesday, January 25th, 2022, and today I sound like a radio announcer, which is fine. Um, I'm going to continue today my talk on hemoglobin and the different interactions that hemoglobin has with the rest of the system. To an extent, we went over yesterday how hemoglobin is stabilized through an external molecule called 2,3-BPG. Oh, by the way, I'm just jumping right into it. No intro today, nothing else. I want to get into it. There's a lot to talk about. Hemoglobin is a complicated protein complex, but it's necessary for life and literally the most necessary thing for life probably out there, one of them, because it delivers the nutrients or the fuel for your body to continue working, your tissues of your body and your cells to continue the respiration through the oxygen that they receive through hemoglobin. So let's continue. So we talked about 2,3-BPG yesterday, which is a small molecule which stabilizes the hemoglobin molecule into its R state from its T state. Okay, we remember R and T states are the two states that hemoglobin can be within. One has the T state being tense and thus a higher energy state, and the T state essentially wants to bind oxygen, O2, diatomic oxygen, so that it can stabilize itself, and essentially that's how oxygen is delivered through your body via hemoglobin and in your red blood cells, right? But the 2,3-BPG, recall, in the situation where oxygen isn't present in adult hemoglobin, you have a pocket of a positive charge in the center of the four subunits of the hemoglobin molecular complex, the alpha, alpha 1, beta 1, alpha 2, beta 2. And the beta chains actually have amino acids within the central pocket as part of amino acid side chains, which cause this positive pocket. So those amino acids are histidine and lysine, and they're essentially spread throughout there's about 6 of them, and they're spread throughout the distribution of amino acids in the pocket, right? So you can see here, these are the amino acids, right? And then the 2,3-BPG molecule, that pocket in adult hemoglobin is large enough such that this 2,3-BPG molecule can come by and kind of be electromagnetically bound within this cage of amino acids that form this pocket, and thus it can stabilize the hemoglobin molecular complex in the R state, right? R conformation, whatever you want, and therefore oxygen will be released from the hemoglobin easier because the hemoglobin is bound and stabilized, right? Like if you go down to a basic stabilization situation, that's essentially one way of allowing the oxygen to dissociate quicker, which then causes the oxygen dissociation curve to shift to the left, right? Because then one of these curves that have DPG or BPG, right, will see no DPG here, and so when DPG is present, then the hemoglobin and these are all at different partial pressures of oxygen, the hemoglobin will bind oxygen, will less strongly be bound to O2, and thus give it up more quickly when it needs to. Okay, so at a lower partial, at a higher partial pressure. Sorry. Okay, so this is a kind of a chart of that. So now that's one way of stabilizing hemoglobin. And that's one external molecular way through the presence of BPG or DPG, however you want to phrase it. But then the second way is called the Bohr effect. So DPG is not the only thing that can stabilize the hemoglobin molecular complex. There's also, you have the O2 that's bound to the top of the hemoglobin molecules. You also have carbon dioxide and H+, which can do the same thing. So the presence of carbon dioxide can actually bind to one of the terminal amino acids to cause the stabilization of the hemoglobin molecule complex, and H plus can actually bind to amino acids to create what's called a salt bridge between two amino acids. So it's recall, we need to go back to what a salt bridge is, right? So basically there's a number of non-covalent interactions within proteins, right? Here's an example to the right of the hydrogen bond, and this hydrogen bond is a fairly strong one. It's not covalently strong, but it occurs between oxygen and hydrogen, and most first year chemistry students are familiar with what happens in hydrogen bonding, and it's essentially why water stays together as a liquid at the temperature it does and pressure it does. But then there's also ionic interactions between side chains within proteins and molecules in general that cause them to be attracted at a certain distance. So at about a 3 angstrom distance, you have these two, in this example, this lysine and this other acid here. They are one is negatively charged and the other is positively charged, and they are electrostatically interacting. The nitrogen is interacting electrostatically with the oxygen, and this is like a carbonyl group right here. So and this is basically where normally an H plus would come by and form an alcohol, but this interaction is occurring here, and this is a strong one, so I assume there would be some competition here. But anyway, without getting too deep into it, that's basically one way protein kind of stabilizes itself. Sorry, an amino acid sequence stabilizes itself, right? Other way being van der Waals interactions, which we're not going to get into right now. But the Bohr effect essentially has that happening with H plus ions and CO2. So CO2 and H plus, they both can get into your system through your respiratory system, right? So Bohr effect, water plus carbon dioxide, carbonic anhydrase, which is something that's in your red blood cells, will form carbonic acid and will allow the presence of bicarbonate in equilibrium by bicarbonate and carbonic acid, which then contributes H plus, right? So the Bohr effect explains how CO2 helps hemoglobin release oxygen into the tissues that need it, because what happens is we go back to the oxygen saturation curves, we see that we have pH here, right? The pH increases. When the pH increases, right, or the pH decreases, that shifts this curve, right? Because that H plus binds to hemoglobin, and thus it allows more oxygen to be released at a higher partial pressure, right? So CO2 also, and the thing to know, right? The thing to know is that as part of this Bohr effect, CO2, without CO2 in the blood and with dissolved CO2, oxygen will be released more quickly. So CO2 does bind hemoglobin, and this oxygen is released at, like, for example, if this is 7 millimeters hydrogen, mercury, 7 millimeters mercury, then this would be releasing a lot. There would be a lot less oxygen present than at on the hemoglobin. Remember, this is what hemoglobin holds onto, right? Having this at a lower, at the same partial pressure, having this value lower than this value means that the hemoglobin is willing to give this up more easily. Okay, so time is not a part of this equation right here, but it's just a note that, in time, as the hemoglobin is transported to a specific area within the body, this curve will be at a certain point, allowing the hemoglobin to be a better releaser of oxygen. And so basically, so that's actually not too much to talk about there. There's also the reverse effect called the Haldane effect, right? So the Bohr effect describes what happens when oxygen is kicked out by carbon dioxide, by H plus, and even 2,3-BPG, right? So oxygen affinity in the Haldane effect is is described in the reverse reaction. Tomorrow we'll talk about the Haldane effect, but just to let you know, just think about it. Think about carbon dioxide's and hydrogen plus ions presence within your blood, right? Because H plus, both these are all talking about exercising tissue, right? In exercising tissue, you have H plus buildup due to lactic acid, right? So the lactic acid's presence will cause oxygen to be released more quickly from the hemoglobin, right? It's also when you have carbon dioxide in your system during respiration, the carbon dioxide transfers over to your blood a lot quickly because carbon dioxide is a non-polar molecule, and when you're breathing in, when you create carbon dioxide byproducts in your body, right, so you can breathe those out, that carbon dioxide, some of that goes over and transfers over to the hemoglobin, right, through all the different barriers and through transportation mechanisms in the cells, etc., and in your red blood cells, and that allows the oxygen that's present to be released more quickly from the hemoglobin. So you're all getting oxygen from the outside within the air, and you're bringing it in, and the carbon dioxide is helping oxygen be kicked off the hemoglobin faster from within your body. So everything is done there in the service of the organism obtaining oxygen more quickly. So that's it for today. Hope that was informative. I know I kind of stumbled through that one, but I'll need a few more iterations on these lectures to talk more effectively about the Bohr effect and other similar effects. So for now, read up on this, and I'll see you around.